Welcome to this session. My name is Renee McCormick. I'm with the National Math and Science Initiative, and I'm really glad you're here. This is the second installment of what I would traditionally call a summer assignment. If you didn't get a summer assignment, maybe you should count your blessings. But in any event, it is sort of introductory material that's not particularly on the AP exam. Now, having said that, what you want to pay attention to throughout this lesson, shall we call it, is the critical thinking that scientists did that led them to a lot of the discoveries and a lot of what we know about the atom and about its structure, which is still evolving, by the way, with more and more technology advances occurring with instrumentation and such. We're still learning that we don't know it all, which is quite humbling. What we're looking at here on this left corner is the Joseph Priestley Medal. It's the highest honor given by the American Chemical Society, which is interesting since Priestley is actually a British chemist, but Priestley is credited with discovering oxygen. Ben Franklin got him interested in electricity. He observed that graphite conducts an electric current. I remind you that graphite is one of the forms of solid carbon. Graphite is the cheap form, obviously. It's what we use to write with. You've probably called it pencil lead, but lead is a misnomer. It's really pencil graphite. Doesn't sound quite as sexy. But in any event, it does conduct an electric current. The other form of carbon solid you're very aware of is diamond. But politics forced Priestley out of England, and he ended up moving to the U.S., and he actually died in the U.S. in 1804. The backside of the medal, which is down below, just kind of interesting, the backside of the medal was given to Linus Pauling in 1984. And Pauling was the only person to win 2 Nobel Prizes in 2 different fields until just recently. And Pauling won one in chemistry, and he also won one in peace. In chemistry, he won it for discovering the primary, secondary, tertiary, and quaternary structure of proteins, which if you're an AP biology student, you can explain that even to your neighbors, but also a Peace Prize. And the Peace Prize was for actually having a worldwide global ban on nuclear testing that was only broken a few years ago. So it was in effect for, I want to say close to 20 years, but don't quote me on that. But it's interesting that Linus Pauling's 1984 date was what is actually chosen to be on the back of the Priestley Medal, which is the highest honor. Most people have Einstein with his fantastically iconic hairstyle as their famous scientist. Mine has always been Linus Pauling. Backing way up to 1000 BC, let's go through some of the more monumental moments, shall we say, with big hops, skips, and jumps through the timeline from 1000 BC to the present day. In 1000 BC, essentially, folks learned to process ores. Now, you know what an ore is, I hope. An ore is basically rock that you cut out of the ground, you dig up, and it has precious metals within it. And so they learned how to dissolve away or dispose of, even if it was mechanical disposal, of the dirt bits in rock and harvest those valuable metal ores so that they could produce metals for weapons and ornaments. We've always had a thing for jewelry, haven't we? And also the use of embalming fluids came into be, not related to metal ores, by the way, but the use of embalming fluids came to be at about 1000 BC as well. 400 BC, moving forward 600 years, the Greeks proposed that all matter was made of 4 elements: fire, earth, water, and air. And you may have read about such things in even your English class as you study ancient Greek literature. Democritus was the first to use the term atomos, which is where the word atom is actually coming from, to describe the ultimate smallest particles of matter. And then for the next 2,000 years after that, alchemy reigned supreme. Alchemy is a pseudoscience, that stands for fake science, where people sought to turn metals into gold. We've always valued gold as a metal. It's bright, it's shiny, it's pretty. And so we have always valued it. You know, it's been the basis of currency for pretty much since the dawn of time when currency began. But these alchemists were great experimenters, and we learned an awful lot of what we know today about chemistry through the plethora of mistakes that the alchemists made, because no one ever managed to turn anything into gold, so pretty much every experiment they did was a colossal failure. Then if we hop forward to the 16th century, which would be the 1700s, George Bauer, a German, refined the process of extracting those metal ores that only took, another 18,000 years. And I'm going to butcher the pronunciation of this one, but Paracelsus, I have no idea how to say that. Apologies, this Texas twang does not wrap well around such a beautiful, elegant name. But he was from Switzerland, so he was Swiss, and he used minerals for medicinal applications. One of the first recorded documents of someone giving someone a chemical instead of believing in, good spirits, bad spirits, God will heal, etc., but actually letting man intervene in trying to cure an illness. And then Robert Boyle is one that you've heard of. Robert Boyle is a British scientist again, and he's the first chemist who is credited with actually performing quantitative, taking measurements, applying mathematics, using numbers to evaluate experiments of pressure versus volume. So you've heard of Boyle's law, P1V1 equals P2V2. And he also developed a working definition for the term elements. So we're not sure who used that term first, because elements, even now, there are elements of writing, there's elements of mathematics. Elements is a very common word in our language, but elements in a chemical sense. In the 17th and 18th centuries, there was George Stahl, who was a German, that suggested this idea of phlogiston, and that phlogiston was this substance that flowed out of burning material. And an object stopped burning, according to him, in a closed container, since the air was saturated with phlogiston, which is a crock, right? The reason a fire stops because you smother it is because it will continue until its immediate environment has run out of oxygen, because it's oxygen that's needed to actually fuel a fire. But phlogiston is a fairly common example of huge misconceptions that permeated through society during the 17th and 18th centuries. Yeah, that's like almost in line with the world was flat. Joseph Priestley is the British chemist who discovered oxygen, which was originally called by all of Stahl's followers dephlogisticated air. So it had been void of phlogiston as opposed to being void of oxygen. So just kind of gives you a perspective that this was a long journey, a very long journey in the evolution of what we know about chemistry, and we're not through with that journey yet. We learn new things all the time. It keeps an awful lot of people employed, and it keeps an awful lot of people working at research universities. So there are some fundamental chemical laws that we're going to explore in this chapter. And these started pretty much in the late 18th century when combustion was studied extensively, right on the heels of the whole phlogiston debacle. The list of elements continued to grow. Things like carbon dioxide, nitrogen, hydrogen, and oxygen were discovered. What was not known at the time is this whole concept of the fact that we had diatomic molecules. We did know some simple proportions, as you'll see here in a few minutes. But Antoine Lavoisier, I love the sound, is obviously French, and he explained the true nature of combustion. And he published the first modern chemistry textbook, which is important. And he stated the law of conservation of mass. Unfortunately, the French Revolution broke out the same year that his text was published, and so he got a little sidetracked. And he once collected taxes for the government and was executed during the French Revolution with a guillotine as an enemy of the people in 1794. They didn't really care about his chemical accomplishments and the fact he'd written the first chemistry textbook ever. He was the first to insist on quantitative experimentation, however, and we do owe him a great debt of gratitude. So, one of the first laws that you've encountered before, hopefully, again, I keep reaching back to third grade because that's when I fell in love with science. I didn't know science existed until third grade, and it happened to be the year of 1968-69. Okay, stop it. Quit doing the math. I am old. And it was that summer of 69 was when we landed on the moon. So the Apollo missions stopped all programming long before cable television. Stopped all programming, and everyone pretty much in the entire country stopped to watch because there was kind of nothing else to do except read a book. And way back, we understood that matter could not be created nor destroyed. So the law of conservation of mass is one of those things that you probably were introduced to when you first started studying science. I'm sticking with third grade because that's where it should be, if not earlier. In 1808, a gentleman named Dalton, as in Dalton's gas law, so John Dalton, the same one, stated a law of definite proportions. And now remember, we got into this concept of actually, with Lavoisier, of putting numbers to things, to quantifying experiments. So he was quantifying experiments and realized, hey, by mass, which was the only thing he had to be able to quantify with, chemicals react in the same way every time. they might react in a 1-to-2 ratio in certain conditions, and if I change the conditions, I might get a 1-to-3 ratio. But if I repeat the experiments over and over, those ratios stick, no matter what masses I start with. So his law is very simply stated as a given compound always contains exactly the same proportions, that being the key word, proportions of elements by mass. Then the law of multiple proportions, as I alluded to a moment ago, reared its ugly little head that sometimes you got a surprise when you were doing all this math. That when two elements combine to form a series of compounds, which may or may not have had very obvious different properties, if they're gases, their properties that are different are not as obvious. But the ratios of these masses of the second element that combined with, let's call it 1 gram, of the first element can always be reduced to small whole numbers. So, for instance, he considered the compounds of carbon and oxygen and determined that he could react 1 gram of carbon at some times and get it to react with exactly 1.33 grams of oxygen, but other times it reacted with twice as much, which led him to this idea of carbon in ratio to oxygen, carbon in ratio to 2 oxygens, which ultimately became chemical formulas, which you know and love in this format. But that's what the formula is actually telling you, right? It's telling you the ratio of the number of atoms, and he just did it in terms of grams, in terms of mass. So just to illustrate that, we have a little example problem here, an exercise, shall we say, where the following data were collected for several compounds of nitrogen and oxygen. So we're switching to nitrogen with oxygen. And we found that in compound A, B, and C, there is a proportion of mass. So, like I said a moment ago, this may be a lesson in essentially the history of what we know about chemistry from sort of the beginning. But honestly, this is the kind of thinking that you're going to be faced with in AP multiple choice questions in particular. So, you'll be given a table like this, and it would rely on your understanding of the law of multiple proportions to be able to actually explain this. So what you want to do as a problem-solving technique is look at the numbers for the sake of the numbers. Identify the smallest, identify the largest. We have some intermediate value. By any chance are these suckers related? Well, don't get tied up in the actual fact that you have 4 significant digits, at least, to look at. Look at a simple proportion. This is about 0.4, this is about 0.8, and this is about 1.8. So more than 0.4, I rounded that much away, is pretty much doubled to get to 0.8. And again, I rounded away, but if we do this, we get an exact fact that going from the 0.8 up to here is also a doubling. So you can think of this as 1 part, 2 parts, and 4 parts. So we would end up with nitrogen, with 1 gram of nitrogen as being perhaps NO versus NO2 for this one and NO4 for this one. So we get a 2-to-1, a 2-to-1, a 4-to-1 sort of simple ratio, but going even farther and looking at the data, we can actually figure out what these proportions are saying to us. Now we would do it in terms of their atomic masses on the periodic table, but I remind you in Dalton's time, that was not to be just yet. He was living before that time. So you studied this in first year chemistry or a previous science class, hopefully, prior to this. I hope this is not a news bulletin for you. But there are 4 postulates of Dalton's atomic theory of matter. No one is going to ask you to state them. We're just going to ask you to apply them. So this is not a memory moment of where you need to actually be able to memorize this and recite it. I would have made you do that in my first year chem class, so you'd know it by now. But all matter is made of atoms, and these atoms are indivisible and indestructible. So here's our big caveat. At the time that Dalton was writing this, we did not know much about the structure of the atom. We did not know anything really about how atoms actually react with one another, and again, the structure within the atom. So this was based on knowledge at Dalton's time. So there are some errors in these 4 postulates, and you've just uncovered the first one. Indivisible and indestructible. Well, if you think about isotopes, and you think about the fact that we can have different numbers of chemical particles or yeah, that's the right word, chemical particles of protons, neutrons, electrons. If we have different numbers of neutrons, we have different isotopes. It's the identity of a chemical is always about the number of protons. So if you think about something like carbon-12, right, it has 6 as an atomic number, so it has 6 protons, and it must also have 6 neutrons. The electrons are so small, they weigh so much less than a proton or a neutron, which weigh fairly close to the same. All of the mass of 12 is attributed to the sum of those two pieces. So there's something that you've heard about too called carbon-14. How are we getting to 14? Well, it's not carbon if it doesn't still have 6 protons. If it moves the number of protons, it moves to a different element. It's got to have 6 protons. So if I take 6 from 14, that means it's got to have 8 neutrons. And this is the radioactive decay carbon that we use in carbon dating. So all matter is made of atoms. It's this part, that they're indivisible and indestructible objects, that is been refined a bit since Dalton's day. But they are still the ultimate chemical particles. All atoms of a given element are identical. Again, I remind you, isotopes exist, so there's another flaw in the present day understanding. In both weight, there's the flaw part, because carbon-14 weighs different than carbon-12, and chemical properties. However, atoms of different elements have different weights and different chemical properties. Compounds are formed by the combination of different atoms in the ratio of small whole numbers. That one is still very much intact. No modification necessary there. A chemical reaction involves only the combinations, separation, or rearrangement of atoms, and atoms are neither created nor destroyed in the course of ordinary chemical reactions. So these remain true to form. The first two have a couple of slight modifications based on what we've learned about subsequent atomic structure models, etc., especially isotopes. All right, so in 1809, a gentleman named Joseph Gay-Lussac, and the hyphen is common in European countries for last names. So don't let that throw you off. So his last name is Gay-Lussac. So Joseph Gay-Lussac, he was French, performed experiments at constant temperature and pressure with gases. I mentioned in an earlier recording, the first in this series, that a lot of what we know about chemistry started with gases because a lot of, shall we say, aristocrats who had time to do their own fun sort of experimentations and things, they really enjoyed hot air ballooning as a sport. And so they were competitive, they wanted to go higher, they wanted to go faster, they wanted to have better control over their balloon, etc., etc. And so they learned a lot about gas laws through this hobby, shall we say. So Gay-Lussac discovered that 2 volumes of hydrogen combine with 1 volume of oxygen to make 2 volumes of gaseous water, water vapor. Vapor is what we use as a term to describe the gas form of something that's typically a liquid at room temperature and room conditions with 1 atmosphere pressure. So 2 volumes of hydrogen we now write like this, right? Except, wait, we know that hydrogen is one of the gens, so it's diatomic. That's my way of remembering what all the diatomic elements are. It's all the gens: hydrogen, nitrogen, oxygen, and all the halogens. With oxygen, also diatomic, to make 2 volumes of water. And to balance that equation, we'd have a 2 there. So he discovered the 2 to 1 to 2 ratio before we ever had this shorthand way of balancing equations. He also discovered that 1 volume of hydrogen, this was not as obvious, combines with 1 volume of chlorine, which is a halogen, to make 2 volumes of hydrogen chloride. In 1811, enter Avogadro, stage left. Avogadro, as in the number you know and love, and the principles that you know and love, the number was all predisposed to this idea of proposing this hypothesis that was a piggyback off of Gay-Lussac's work, he admitted. He basically was ignored for 50 or so years, but his hypothesis said at the same temperature and pressure, equal volumes of different gases contain the same number of particles. This was the dawn of his experimentations that led him to the famous 6.02 times 10 to the 23rd, the number of particles in a mole of a substance. And we spell it M-O-L-E. Excuse me. You'll often see it abbreviated MOL, which is fine, but mole, not the adorable furry little creature that lives below ground for us, but mole originally, I think it was the Greek language, but don't quote me on that. Essentially, it means a heap, a bunch of particles. But his gas law stuff came first. It led him to moles. Also led him to molar volume of a gas. That what he knew to be true is that at the same temperature and pressure, equal volumes of different gases contain the same number of particles. They also, therefore, occupy the same volume, which he later determined to be 22.4 liters per mole of gas. So he was really all about quantifying. All right, you could spend an entire semester studying the history of chemistry. We're just going to hit the high points, again, so that some of these classical experiments may serve as data sets for you to have to analyze. And so knowing a bit about the experiment would assist you, shall we say, in reaching the proper conclusion, which would assist you in being able to analyze the data properly. So, based on the work of all of these predecessors we just discussed, Dalton, Gay-Lussac, Avogadro, among several others, chemistry was beginning to make sense, even if you don't agree, and the concept of the atom was clearly a good idea. This idea that there was this one fundamental little piece. The electron was discovered by J.J. Thomson. Note there's no P in that. That's not a typo. It's a British last name. Working in the late 1800s and very early 1900s, he found that when high voltage was applied to an evacuated tube, a ray, he called it a cathode ray. And he called it a cathode ray since it emanated from the negative electrode. All right, I got to have a moment with that. When we study electrochem, you're going to learn that when we are inside the battery, when the chemistry is happening and the chemistry is inside the battery, that the cathode is a positive electrode. Easy to remember because that T in the middle of cathode looks like the way a first grader would write a T, but it's also a plus sign. When we use the battery, which is what Thomson did, he found that when high voltage was applied, that means he used a power source, a battery of some variety, as you will. When we're outside the battery, the polarity of the cathode and the anode switch. So when we're inside the battery, when we study our electrochem unit, our cathode will always be positive, our anode will always be negative. But the minute we use the battery as an outside power source, the polarity of those have to switch, because if you think about the way the electrons are going to flow since opposites attract, I need a negative electrode that's going to actually be the cathode. So that's why this was called a cathode ray, since the ray emanated from the negative electrode. And that's what I mean when I say when you apply voltage, when you're using the battery to power this. So the salient points are the ray was produced at the negative electrode, repelled by the negative pole, then, of an applied electric field, and he postulated that the ray was then a stream of negative particles, which we now call electrons. So he figured out the charge before he actually named the little sucker. He then measured some deflections, and I'll spare you all the physics, but he measured some deflections, and you can see that this ray goes nice and straight until it reaches this applied field. And there's a positive end up here, so there's lots of positive charge on this plate, and there's lots of negative charge on this plate, and the particles are attracted upward to the positive, which means they themselves would need to be negative. So you can look at it two ways, can't you? Opposites attract, likes repel. So thinking about it both ways. If this is the positive end of the electric field applied, and these rays are moving toward it, then they themselves must be made of negative charge, and vice versa. If they're moving away from this negative end down here, they must be repelled. So either way, both of those postulates hold true. Opposites attract, likes repelled. So he determined that the charge on these particles was negative. He eventually called them electrons. What he didn't do initially was get the mass to charge ratio. That came later. That was a whole different set of experiments. So E is the charge on the electron in coulombs, and m is its mass. So in this course, when you see the little baby cursive E, you should think about the fact it has a charge in coulombs and it has a mass. Thomson also discovered he could repeat this deflection in calculation using electrodes of different metals. This wasn't specific to just a single metal. All metals contained electrons, and all atoms contained electrons. The cool thing about metals is if you have a clump of copper, you have a little piece of copper, then it really exists as ions. Plus ions and minus ions. And around those ions are the equivalent number of electrons to keep this situation neutral. But these electrons are free moving. If he'd have chosen something other than a metal to experiment with, he'd have gotten discouraged very quickly. So I don't know enough about his history to know if he was just lucky and picked up a metal to try, because liquids and gases are far, far more difficult to hold and handle, so it's kind of the obvious choice, or if he even thought about that. But I'm sure he did later think about that, because we do now know that this is how metals exist. It's why they're such good conductors of electricity. If you bombard them with incoming electrons, it's almost like this is a pull cue hitting this piece of metal, and it's going to displace an electron, and they're going to collide with other electrons until eventually they're ejected out the other end. Not the electron that came in first, but one of the metal's electrons is ejected out the other end. This is a cathode ray tube animation. So we have this beam of light. You can see the beam of light at the top of the screen. A magnet is being brought into the field of view. And now they've switched the magnet around so that the opposite pole is at work. So you can see that the ray particles are being deflected. Now, it's a horseshoe magnet. I don't know if you can tell that exactly, but now the magnet is being moved closer back to the source, and you can see that the particles are still attracted to it and still deflected from it, but they are able to shorten the beam this way. If they would flip it back around, we'd see it coming back up toward the top like we did at the beginning. All right, so he also knew that furthermore, that all atoms were neutral, so there's got to be some positive charge within the atom, and the plum pudding model was born. He knew that the pluses and the minuses had to equal out if this was going to be a neutral chunk of matter. And so just a caveat on this plum pudding thing, because I know when I was a student I was like, plum pudding? Really? Because plum pudding would be like no particles in it at all. No, I didn't know this until I moved to England for a couple of years. The Brits call every dessert pudding. You're going to have a piece of pecan pie? That's your pudding. So you may eat your dessert, your pudding that the Brits call it, with a knife, a fork, a spoon, all of the above. And so we would call what they call plum pudding something more like raisin bread, where the raisins were like these electrons that were randomly distributed throughout this positive bread. So it's like a raisin bran muffin kind of thing. That confused me when I was a kid. I later learned what the heck that meant. So one of Thomson's greatest contributions to modern science was his role as a highly gifted teacher. Okay, that makes me happy, since I've devoted my adult life to this. So a highly gifted teacher. And I haven't been this gifted because he had 7 of his research assistants, Rutherford among them, we'll talk about in a minute, and the aforementioned son. There was a son of this. The Thomsons are one of the only father-son pairs to both win Nobel Prizes. I think it's happened one other time, but it's amazing that you can have a Nobel Prize winner produce a Nobel Prize winner. But they won Nobel Prizes in physics. His son won the Nobel Prize in 1937 for easy for me to say, for proving the wave-like properties of electrons, that electrons behaved as waves as well as particles. And he is buried close to Sir Isaac Newton in Westminster Abbey. That's one of the highest honors that you can get if you're a British scientist, is to be buried in Westminster Abbey, along with all the royalty. So here's what he did, essentially. And again, the only context that you would need to do this is to be able to sort of explain something if you saw a similar experimental apparatus. He had a microscope lens, so he could see these tiny little deflections and particles. He had an atomizer. You need to think about like an old-timey perfume bottle. It has a rubber bulb on the end, and you squish the rubber bulb, and then that puts a fine mist of liquid particles into the air. It's called an atomizer. So what it did was produce some oil droplets, and then he could run X-rays through the charge to produce charges on the oil droplets, and then he could do the physics calculations to figure out the charge to mass ratio. And so pages and pages of calculations later, we accept that the mass of an electron is 9.11 times 10 to the 31 minus 31 kilograms. That would be 0.31 zeros before you got to the 911. Now, in 1909, Millikan is the scientist that did this, and he halted their fall due to gravity by adjusting the voltage across the plates. So he basically had them suspended in air, or a vacuum chamber, I guess it was really, had them suspended, though, using electricity to do it. Just the right amount of repulsion and attraction so that the particles would sit still. And so that way he could ultimately go through all the calculations and get that mass-charge ratio for the electron. And then, of course, radioactivity was a hotbed of research at the same time in the early 1900s, and Henri, is how they would say it, Becquerel, French, found out quite by accident, which, we often in science use the word serendipity. I think of that as translating to the idea of a happy accident, a serendipitous discovery. It's like, aren't we fortunate? For instance, there's this drug called cisplatin that they were using to do something completely different with in laboratory rats, and what they discovered was that any of the tumors on laboratory rats that received cisplatin started shrinking dramatically, and that was the first chemotherapeutic agent that we use to this day to fight cancer. So when someone's undergoing chemo, we're pumping chemicals into them that are designed to kill the tumor without killing the patient. And cisplatin was the first one that we ever used, and it's like 98% effective on curing testicular cancer in particular. So serendipitously, he found that a piece of a mineral containing uranium could produce its image on a photographic plate. This was because he was a slob. He stuck one of his samples inside a desk drawer because someone was going to visit his lab and he hadn't done his proper housekeeping, and he had some X-ray photographic sorts of plates in there, and it ruined them. And so then he was like curious about that. So that's the happy accident part. And so it can produce its image on a photographic plate in the absence of light. Normally we have to have light to make a photograph. This was a different way to do it. So he called this idea radioactivity, and ultimately it would lead to this idea of X-rays. How we use X-rays currently. You take a film, shine an X-ray through it, and then you get this black-white kind of image that has enough contrast you can make out body parts. So he attributed it to this spontaneous emission of radiation by the uranium in the mineral sample, which was a good assumption, because you know that uranium is radioactive. Matter of fact, it's the last naturally occurring element on the periodic table with an atomic number of 92. Anything beyond that's been man-made, but we also know it to be radioactive. There are 3 types of radioactive emission. The AP test does not dwell upon this, but just your general scientific learning, you should know these things. So an alpha particle is equivalent to a helium nucleus, which is gigantic. It's the largest particle on this subatomic scale that is emitted, and it's 73,000 times the mass of an electron. We symbolize it this way, or we also symbolize it as an alpha particle with the Greek letter for alpha. And since these are larger than the rest, they're not as dangerous. They're not as penetrating. We can stop these fairly easily. Your clothing would essentially stop alpha radiation. So early atomic studies often involved these. Beta are much, much, much more dangerous. They're essentially an electron. So a beta particle can be symbolized by either the Greek letter beta or this idea of an electron using E, but it has essentially no mass. So the top number is the mass, but it does have a charge of -1. Note that the alpha particle was neutral. And then a gamma ray is no particle at all. It is pure energy. It is the most penetrating, the most dangerous. This is what causes devastation when there are radioactive accidents. So it would take a foot of lead, a foot of concrete and several inches of lead, I think it actually is, to stop the penetrating power of gamma radiation. All right, so eventually we're coming around to the 1911 era, and Ernest Rutherford in England had pretty much figured out what an atom, or so he thought, looked like, what it was going to be, how it was going to be assembled, for lack of a better term. So he was a pioneer in radioactive studies, and he carried out all kinds of experiments to test Thomson's plum pudding model. The plum pudding model was pretty straightforward. It was this idea of there were positive charges, and since the atom was neutral, there had to be associated negative charges. I would need 5 of them to stay true to my drawing here. And they were just randomly arranged just the way the raisins were in a Raisin Bran muffin type thing. So Rutherford was doing some experiments because he just wanted to test this. He had a feeling this might not be correct. And so he, was trying to make sense of things. So what he did was direct those big alpha particles at a thin sheet of gold foil, the thinnest sheet you could. So imagine like aluminum foil. You've seen it before. There's probably some of it in your kitchen. Go even thinner than that. The thinnest piece of foil you could get that wouldn't just tear when you handled it. And he thought that if Thomson was correct, then those massive alpha particles would blast through the thin foil like cannons through gauze, because we knew that the atom was a lot of empty space. So he actually had a pair of graduate students, that one of which at least you may have heard of, Geiger, as in Geiger counter. I mentioned that Rutherford studied radioactivity, right? Geiger and Marsden do the first rounds of experiments, and he expected those alpha particles to pass through with minor and occasional deflections. Oh, but that's not what happened. The results were astounding. Poor Geiger and Marsden first suffered Rutherford's wrath and were told to do it again and again and again, since this couldn't possibly be. So the apparatus is shown down here below. We have a source of particles, and they're concealed? They are concealed in cement, so they're not damaging the experimenters, the humans involved, but they're emitting a beam of particles. And then they made this screen that was going to detect the scattering of these particles. And so some of the particles did scatter. That was expected. Most of the particles, however, passed straight through, which didn't surprise Rutherford, because that was one of his hypotheses, was that the atom was mostly empty space. But what surprised the heck out of both Geiger and Marsden was the fact that on occasion, every once in a while, one of the particles would bounce directly back at them. That was inexplicable. They couldn't come up with a reason for that. But the data is the data, and they were the lowly graduate students that took him to the grand professor. And of course, he berated them and said, "You fools, go back and try again and again and again." So finally, he stormed down to the lab himself and he said, "Show me." And indeed, it was undeniable. They were bouncing back. So now you've got some splaining to do. You got to figure out what happened. So Rutherford has a famous quote that it was like shooting a howitzer at a piece of tissue paper and having the shell reflected back. Hopefully you learned what a howitzer was. It was a big, giant, rapid-fire gun back in that time period with these gigantic shells. Think of like bullets on steroids. And so for that to go up to a piece of tissue paper and bounce all the way back was just ridiculous. And that's why he was having a hard time processing it. So he knew, though, from this, he knew one thing. He might not have known how an atom was arranged, but he did know that the plum pudding model could not possibly be correct. So then he did further studies, and those particles with the large deflection angles had what I would call as a close encounter with a very dense positive center of the atom. So he came up with this idea of this dense positive center, which ultimately was called a nucleus. Leeuwenhoek had discovered the microscope many years earlier, and people were looking at cells, and cells have a nucleus, and so that term just kind of stuck. It had a scientific connotation back then, rather than a colloquialism as it might now. We talk about the nuclear family and this and that. But he conceived this idea of this very positive, very dense center. So here we have a picture, for lack of a better term, animation for the apparatus that's emitting the alpha particles in Rutherford's gold foil experiment. This is going to be the path of the particles, or at least what he expected. Obviously, that's our very thin slice of gold foil. And this whole screen is actually a detector made out of zinc sulfide. Not that anyone's going to ask you that, but just in case you're curious. So what's going to happen is that these radioactive particles are going to light up. So you're going to watch for these little red blips on this screen. There's one. And so it's detecting the path. Note that what they expected to happen was that most of these would just go straight through the gold foil. But much to their surprise, that's not exactly the way it went. All of a sudden there started to be some deflections, and every once in a while, one would bounce all the way straight back. Very unexpected. And this got Geiger and Marsden into a lot of trouble. They had a lot of explaining to do to their boss, Ernest Rutherford, who sent them back to their lab and said, do it over and over again, like we talked about just a moment ago. So now, just to kind of enlarge this, here's the particulate view, what we expected to happen. They sort of knew that all these little green dots are going to be our alpha particles, and these are the small positive centers that we'd pretty much already established existed in a chunk of any element, in this case gold. And so they're expecting that some of these particles on occasion would hit and be deflected, but that most of the particles would go straight on through. And so indeed, as they start them off, this is just a different view. We've got these big spheres because this is a pretty dense metal, so there's not a lot of empty space between what everyone thought were these sort of, for lack of a better image, round balls, and that essentially these little particles, these little alpha particles, would just slip right on through. Every once in a while, they would come in contact with a center and actually deflect, like we just saw. And so they tried this with several metals. Gold wasn't the only one. But again, here is what's happening with our apparatus, and for anything to bounce back was quite surprising. So every once in a while, like you just saw, one would be deflected, but most of them would go through. It was a pretty narrow thing for them to hit. But on even more rare occasion, one would hit and go straight back. That was the most perplexing part, the straight back reflections. Or deflections, I guess is what I really should say. And so they had to explain what it was that was causing these deflections to come straight back. They understood what was happening when it would, by chance hit the metal detector. But again, most of them were supposed to go straight through. Very few particles would actually do this, but deflected backward was totally unexpected. So they had to rethink what they thought was going on inside the actual structure of this material. So in order for something to be deflected, it had to come mighty close to that little positive center. And opposite charges repel. So this situation would cause a deflection of maybe 20 degrees or so. They had lots of data to analyze, and that would seem to be the normal pattern. But every once in a while, whammo, one of them would go straight back. That was the perplexing bit. So then they came up with what was called the planetary model, where there were these orbits, like the planets orbit the sun. This is the thing where I'm trying to get out of everyone's brain. This has been ingrained in science texts for far too long, because the reality was they did the calculations and they figured out it would take about 10 nanoseconds for, if this were the true model, for this electron that's orbiting around this positive nucleus to collapse. Because, let's see, opposites attract. Even if you put the particle in motion, it's going to basically be drawn into the center. So about 10 nanoseconds. And so this center contains most of the mass of the atom, while the remainder of the atom is primarily empty space, and so the electron cloud was born. Those were not his words, but the concept was born. So this picture just shows a contrast of electrons being scattered throughout a diffuse positive charge region, as opposed to having this clearly defined, very localized center of the atom with this very positive center, and the electrons still being diffused out in the rest of that region of space. It is wrong to always think of atoms as spheres, but I know that you have been bombarded your entire life with images that way, and you're going to continue to be bombarded that way, but you need to think of them more as a fuzzy region, not like a hard sphere like a ball. That's a misconception. This picture is better because it shows you the fuzzy edges. It's more of a region of space in 3 dimensions, which is hard to actually get onto paper. All right, so what's our modern view of the atom? Well, all matter is composed of one and only one type of atom, and that's called an element, and there are 92 naturally occurring ones, as I mentioned earlier, uranium being the last of those. All others are synthetic or man-made. So the atom is indeed the smallest particle of an element that retains the chemical properties of that element. We have a nucleus that contains the protons and the neutrons. Again, I know I'm insulting your intelligence. You probably know all this already, but that's the whole point of a quick review. So the electrons are located outside the nucleus. The diameter is roughly 10 to the minus 13 centimeters. Not that you need to memorize that or anything. But the electrons are located 10 to the negative 8 centimeters from the nucleus. Well, that's a pretty hefty distance. So a mass of nuclear material the size of a pea would weigh 250 million tons. Let that sink in for a minute. Remember, a ton is 2,000 pounds. That means it's very, very dense. To give you a better analogy, my favorite analogy, being from Texas, involves, well, football, because it is close to a religion here in this state. If you can imagine a football stadium, a big football stadium, a high school-sized football stadium, not something like, the New Orleans Superdome, but a nice football stadium, like at your own high school. The nucleus would be basically the size of a flea placed on the 50-yard line between the hash marks, and the entire rest of the stadium would comprise the rest of the atom. So it just gives you an appreciation for how very small and thus how very dense the nucleus must be if all of the protons and all of the neutrons are compacted in there while the electrons run around free in that other space we call the electron cloud. So you probably already know that protons are positive. They both start with P, positive and proton, and responsible for the identity of the element. You change the number of protons, you change the identity of the element, and that's called the atomic number, that number of protons. Neutrons are neutral. They have no charge whatsoever. They are roughly the same size and mass as a proton, but they are responsible for isotopes when we talked about carbon-12, carbon-13, carbon-14. All of them have 6 protons, but they have 6, 7, and 8 neutrons, respectively, to make 12, 13, and 14 the answer to the sum of the number of neutrons and the number of protons. The electron in a neutral atom will also be the same as the number of protons. They have a negative charge, so if you have as many pluses as you have minuses, then the atom is going to remain neutral. If you remove some of those, we can start talking ions. They're the same size as a proton or a neutron, roughly. Okay, that was shocking to me when I learned that. Really? They've got all that? Yeah, really? They're so much less massive, but they're about the same size as a proton or a neutron, but they're much lighter, about 1/2000th the mass of a proton or a neutron. And they're responsible for all the bonding that occurs. Hence the reactions, the ionizations, etc. The electrons are easily added or removed to make those events take place. So then, of course, we love our symbolization. So the atomic number is usually symbolized by Z, and the mass number usually by A. And the atomic number, again, I remind you, is the number of protons. So X here is my fictitious element, and then the mass number is usually reported here. That's the number of protons. And the atomic number, which is equal to the number of protons plus the number of neutrons, is the subscript to it. So just a symbolization that you'll be seeing from time to time. So again, note that the mass of the proton and the neutron is about the same. To 3 significant figures, it is the same. But look at the difference in that electron. 10 to the minus 31 versus 10 to the minus 27. And I can't remember if these are kilograms or grams, but I kind of think they're kilograms. Alright, so this is just some practice on writing the symbol for atoms. Write the symbol for an atom that has an atomic number of 9 and a mass number of 19. So 9 and 19, and we're looking for what that symbol would be. How many electrons and how many neutrons does this atom have? Well, it has 9 electrons, since it has an atomic number of 9, which means 9 protons. And if I subtract 19 minus 9, then it must have 10 neutrons. Alright, so let's go find out who that is. If I were smart, I'd have a periodic table up and running, so bear with me a moment while I get one going. Thanks for your patience. Alright, so who is element 9? 1, 2, 3, 4, 5, 6, 7, 8. Found it. It's fluorine. Notice also that it has a mass of 19. This is the official periodic table on the AP exam. You need a copy of it. Note that all of the molar masses are reported to 2 decimal places, and note that gotta get down here. Number 92 is the last one that has a mass that is not in parentheses. See, I wasn't lying to you. It is the last naturally occurring element. It is radioactive, though, as well. It doesn't mean that you can't be radioactive just because you're naturally occurring. So we're talking about our good buddy fluorine here. Let's see if I can get back to where I was. There we are. So the symbol here should be F. Did I do everything they wanted? Write the symbol for the atom. It has an atomic number of 9 and a mass number of 19. How many electrons, how many neutrons does this atom have? So if you'd have just written F, you would have been fine. You would have answered the question asked. Isotopes. Isotopes are atoms having the same atomic number as we talked about earlier, same number of protons then, but a different number of neutrons. So most elements have at least 2 stable isotopes, but there are a very few with only 1. Do not memorize these, it's just interesting. Aluminum, fluorine, and phosphorus, for whatever reason, don't particularly have isotopes. Oh, they have only 1 stable isotope. So if they have an isotope, it certainly doesn't last long. That's what the stable part means. So hydrogen's isotopes are so important they have special names. So when there are 0 neutrons, it's really just a single proton and a single electron, which is your good old garden variety hydrogen atom. We just call it hydrogen. But if you add that neutron, instead of hydrogen having an atomic mass of 1, it now has an atomic mass of 2, and the French for 2 is deux. So deuterium is its name. I mentioned that Henri, who was one of the early researchers of radioactivity, was French. So it makes sense. And then if you have 2 neutrons, now you have the mass of that one proton to make it hydrogen plus 2 neutrons, so now it weighs 3, and they call it tritium. So you're used to tri being a prefix for 3. You just may not have been used to deux as being a prefix for 2. But if you play cards at all, you might call a 2 a deuce, and that's how I remember it. My grandpa raised me, taught me to play what's now called Texas Hold'em at the age of 5. Told me it was rummy. My grandma was not happy. All right, molecules and ions. Electrons are the only subatomic particles involved in bonding and chemical reactivity. The sooner you embrace that, the easier your life is going to be in the rest of this class. Chemical bonds are forces that hold atoms together. They are attractive forces. They are electrostatic forces, meaning pluses and minuses, and they come in different degrees. We'll have a whole unit on just the different degrees of chemical bonding. There are, what you know already, hopefully, is that there are covalent bonds where electrons are shared. And these make independent units. So a pair of hydrogens are sharing electrons to make H2. Hydrogen is sharing its lone electron with oxygen twice, 2 different hydrogens, to make a stable compound called water. The same for ammonia. And you're going to have to give up and just accept the fact that we call this ammonia. Because when we talk naming in a minute, first of all, it's written wrong. You should have put the H first the way it is in water. But secondly, it would be trihydrogen nitride, and no one calls it that. It's called ammonia. And methane, that's another one to learn, that you just need to know the name methane. To name a few, oxygen as well. A molecule is the smallest unit of a compound that retains the chemical characteristics of the compound. All of the constituent properties and characteristics of the elements are lost. It gives up its identity once this happens. And then molecular formula, you use symbols and subscripts to represent the composition of a molecule, like we just have written up here above. And then structural formulas. You need to enhance your three-dimensional thinking. There is a gentleman, a researcher named last name of Gardner. And Gardner published, at least 25 years ago, this concept of the fact that the human brain has at least 7 intelligences, multiple intelligences. Music is one, artistic ability is another, mathematical ability is another, etc., etc. I was shortchanged on the artistic side and the music side. But one of those 7 intelligences is spatial. And it's one of the last ones that develop. And so do not beat yourself up if you can't yet take a diagram on a flat sheet of paper, bring it up into space, and rotate it in your mind like a hologram in 3 dimensions. That will come to you. And I have my own postulate on this. I believe that your spatial intelligence begins to develop exponentially, very, very rapidly, once you sit behind the wheel of a car and you become the driver. So the longer you drive, for survival reasons, your spatial intelligence improves dramatically. The more you've played sports and had objects hurling your direction, coming at you at very fast speeds, you've improved your spatial intelligence. So if you can't look at these and see these molecular structures off of this flat piece of paper, then don't beat yourself up about it. All right, ions. Ions form when electrons are lost or gained. And remember, electrons are negative. So cations are positive ions, often metals, since metals lose electrons readily to become positively charged. Anions are negative ions, which, go figure, are often the opposite of cations, thus they are the opposite of metals, so thus they are usually nonmetals, because nonmetals gain electrons to become negatively charged. So your good buddy sodium chloride is pictured over here at right. So sodium chloride is an ionic salt existing of chloride ions, which are large. Why are they large, you ask? I'm so glad you asked, because it gained a particle. It gained an electron. You certainly can't gain protons or neutrons. They're locked up tight in the nucleus. So the only thing it can gain is an electron. But wait, electrons already existed there. So now you have an invading electron, it's more crowded, and what do like charges do in the company of one another? They repel. So poof, the size of the chlorine atom, when it becomes a chlorine ion, that size increases. Sodium is the opposite. Sodium lost an electron. Well, sodium has got now more protons that can pull more tightly on the remaining electrons in the cloud, since now it's down by one player, and it shrinks. It pulls that electron cloud in more tightly. You're also going to learn where cation and anion got their name when we talk about electrochemistry. Something to look forward to, figuring out why we call them that. All right, polyatomic ions are units of atoms that behave as one entity. I maintain it is worth memorizing 9 polyatomic ions and 3 patterns. I'm going to put that on a separate handout. It's going to be a separate screencast. But it would behoove you, that means worth your while, to go out and learn those 9 polyatomic ions. The God's honest truth is you probably already know half of them anyway. You might even know all of them from your first year course. But 3 patterns will greatly expand your knowledge of polyatomic ions. Ionic solids are held together by the electrostatic forces. Opposites attract, pluses attracting minuses. And we can actually calculate the magnitude of them using Coulomb's law. There was a scientist named Coulomb who figured out that opposites attract and actually applied the mathematics to it. You will study this in a physics class for certain, but we're also going to study it in some detail here in this class. When these electrostatic attractions are strong, the ions are held together tightly and close together as well, and that makes them solids. Phase is all about the strength of intermolecular attractions. Inter, prefix meaning between, and interstate highway. That's a highway that goes between states. An intermolecular force is a force that occurs between molecules. So the intermolecular forces that hold molecules together, never to be confused with the intramolecular forces that hold molecules together, which would be actual bonds. IMFs, intermolecular forces, are just electrostatic attractions. But either way, when it's ionic, or when we're trying to get our head wrapped around the magnitude of an intermolecular force, then we use Coulomb's law. Now, in its strictest sense, I just boxed it here in blue, it has this constant, and you can actually calculate this. Well, we want to deal with it more qualitatively than quantitatively, so basically you just need to embrace the fact that it's a force. It's going to have a sign on it, because when opposites attract, the Q1 and the Q2, the Q represents quantity of charge, Q for quantity. So one would be positive and one would be negative, and if I multiply a positive charge times a negative charge and divide it by a positive distance and square the positive distance, which remains a positive number, then aren't I going to end up with a negative sign on that force? Yes, I am. So when the force is mathematically computed as negative, then it's an attractive force, which we show over here. And when it's greater, it's repulsive. More than you needed to know. You just need to know that the force of attraction, whether you put an algebraic negative sign on it or not, is proportional, that's a proportionality sign, proportional to the product of the two charges, plus 1 minus 1, plus 2 minus 2, plus 1 minus 2, which then is divided by the distance between them squared. The larger they are, the greater the distance between them. So when they're close together, you get a great force, and when they're far apart, you get a weak force. Now we're going to move into an introduction to the periodic table. This periodic table is very colorful, but one of the things that hops out at you right away is this stair step. You probably have learned in a previous science class that this stair step separates the metals from the nonmetals, with all of these down here being the rare earth metals. And technically, they are sandwiched right in here. And technically, that means these two guys would come off right over here. Most periodic tables don't show it that way, but if you look at the numbers, you're going from 57, you come down here to 58. Going from 89, you come down here to 90. So that really should be where Rutherfordium is, RF. All right, so metals, nonmetals, metalloids, meaning they have some metal and nonmetal properties. One of the The metalloids are on either side of the stair step. Silicon has revolutionized our current existence, being a metalloid. It's conducting electric current, but technically it's a non-metal. So the things that are on either side of the stair step, adjacent to that stair step, snuggled up next to that stair step, those are our metalloids. Then, when you were first introduced to the periodic table, you had a devil of a time learning some symbols, because their symbols make no sense, in the English language anyway. Copper. It doesn't have a U in it, but its symbol is Cu. Iron doesn't have an F or an E, but its symbol is Fe. Well, that's because they got their name from their original Latin name. And in the Latin name, they kind of make sense when you look at them. No need to memorize, just pointing it out to you, so if anyone ever asks you, you can answer that question. So the atomic number, once again, is the number of protons. It's written above the symbol in the periodic table. The mass is often written below. The one for the College Board AP exam is got the masses written below, like we just saw, to 2 decimal places, except for the ones in parentheses, which the parentheses are saying, hey, these have a half-life so dang short, we can't get an accurate mass on them to 2 decimal places. Metals. Metals are malleable. That means you can mush them around, so you can bend a metal. You can hit them with a hammer and they dent. That's what malleable really means. So you can hammer them into thin sheets. That's why we call it sheet metal. And then ductile means that I can take the metal and I can pull it through. It's very, very soft in a way, so I can pull it through and make a wire from it. So ductility means it can be made into wire. If you think about conduction and electrical conduction through a wire, ductility, the word, makes a little more sense to you. And they also have luster. They have a shiny appearance, most of them. Lead isn't all that pretty, but most of them are bright and shiny, and you can polish them. Now, if they're not bright and shiny, it's because the atoms on the surface have reacted with the oxygen in the air and oxidized. So, if you've ever had to polish a piece of silver with silver polish to get the black, ugly tarnish off of it, then you have removed the silver oxide from that piece of metal. And you had to use chemicals to do it, and they're often stinky chemicals. They smell kind of sulfur if they work well. So we talk about a patina, which tarnish is a patina, or tarnish is an oxidation. Patina is often used with copper. When you look at the Statue of Liberty, she appears green. Well, she's really made of copper, which doesn't appear green at all, but she's out in the middle on an island, and she's actually been oxidized quite a bit since, I guess it was, I can't remember what year they actually redid her. They reskinned her at one point. But in any event, she's turned all green, so that's the patina of the metal. All right, so the groups or the families, the vertical columns, have similar and physical and chemical properties. There are a few of them that you need to know by name. The alkali metals are the 1As, so they're right here. These are the alkaline metals. Why? What does alkali mean to you? It should mean the opposite of acid. So acids and bases, we also call bases alkaline solutions. It means that if I take these metals and I put them into water, they actually react with the water, some of them quite dramatically. The smaller they are, the more dramatic that is. But what is left behind is a basic, as in not acidic, as in pH greater than 7 solution. So you need to know those. And then we talked about the halogens. They're group 7A. And the noble gases you probably already knew. Over here. They have a full octet of electrons, and they are essentially unreactive. Now, naming simple compounds. I'm going to take you through this very quickly. If you already know how to do this, by all means fast forward. But you might want to hesitate when you get to the acid part, because that may be something you didn't have as much experience with in first year. So go ahead, you're not going to hurt my feelings. Fast forward all you want. Binary ionic compounds, naming positive ions, which are usually metals. If it's monatomic, it's usually a metal. It's a cation. We simply use the name of the metal from which it was derived. So Al3+ is the aluminum ion, and its transition metals form more than one ion. We use Roman numerals in parentheses following the ion's name. The Roman numerals are your friend because they are telling you the charge on that species. So if I'm looking at the words copper Roman numeral 2, and by the way, that's not a typo, you're going to see this in print more incorrectly than you will see it correctly. There really is supposed to have that Roman numeral snuggled right on up to the name of the metal. So this 2 is telling me that this is +2. So it's my friend. And then Mercury 1 is the only exception to that, because Mercury is a freak anyway because it's a liquid metal. And so you can have diatomic metal, Hg2. It's bizarre, but Mercury's bizarre anyway since it's liquid. And so it comes in Hg pluses that are associated together. And so Mercury 1 really does have a Roman numeral 2. The AP exam is not going to torture you with that. Let it go. I just have this need to fully educate you. All right. That Roman numeral thing, yeah, it looks strange, but it's all because of Mr. Stock. Mr. Stock back in 1916 published this naming system, which I actually say I like. I like it better than the old system. The system before that was you had to memorize a bunch of stuff. There was cupric, and there was cuprous, and one of them was the +2 variety, one of them was the +3 variety, and I could never remember which prefix went with which. And so ferrous, ferric, stannous, stannic for 10-2 and 10-4, etc. You also need to know ammonium. Ammonium is our only positive polyatomic ion that is on the most of the common to memorize lists. It's one of the 9 that I mentioned that you should memorize. And again, that's going to be a separate recording. I know you just can't wait to get to that one. But no Roman numeral is used with silver, cadmium, or zinc, even though they reside in the transition metals, which is where all the other Roman numeral ones reside. These 3, you just have to kind of give up and know that zinc is always a +2, and the other 2 are always, silver is a +1, and cadmium and zinc are always +2. So I put them in alphabetical order by symbol to remember that. I have all kinds of silly ways to remember stuff, but hey, it works. So the first is 1 and the other 2 are 2 is how I remember that. So if you can remember, just work on remembering silver, cadmium, and zinc, put their symbols in alphabetical order. First one's 1, the other 2 are 2. They only make one valence state, and that's a discussion for when we actually do the periodic table unit. I'll explain it in gory detail. Once again, I know you can't wait. All right. So if it's a monatomic situation, we're going to add the suffix "-ide" to the stem of the nonmetal's name, and the halogens are called the halides because we write the positive ion. That doesn't look like the word ion, does it? And the negative ion. Now, there are some exceptions to this. So if we think about this compound right here, then we would have dihydrogen monoxide, but no one really calls it that. We call it water. So there are some you have to kind of give up and use the common name for. If it's polyatomic, then which is quite common, the oxyanions, the ones that have O's in them, are the polyatomic ions that contain oxygen. I just said that, go figure. So hypo versus ite versus ate versus hyper. Okay, this is a little bit annoying, but it's easy to memorize. I'm going to start at the bottom though, because the word hyper has been used for well over a decade now to describe, well, children and other age groups of adults. They're hyper. What does that mean? Well, what is hyper short for? Hyper is short for hyperactive. So they can't sit still, they fidget all the time, they might have trouble focusing, etc., etc. So hyper is often in chemistry made into a contraction where they simply leave off the apostrophe, which is somewhat annoying. And so we take the HY off and we should contract it as per something like perchlorate, but instead we don't. But hyper is where it really comes from. And then I have this silly little way of memorizing things when it comes to the polyatomic ions. Those 9 that I keep referring to, I memorize the ites because the ates ate another oxygen. So if I think about nitrite, which I have memorized, is NO2-, then nitrate I get for free because it's the same charge, but it ate another oxygen. So anytime you have an ite-ate thing going on, here's another one. Sulfite. I've memorized it's SO4 SO3 2-, but sulfate Same charge, just ate another oxygen. I also remember that it's a 2 because the S looks like a backward 2 to me. It's a warped brain, but it works for me. All right, come up with your own system. All right, so the 8 version ate the least oxygen. The 8 ate one more oxygen than hypo, and the 8 ate one more oxygen than the 8, and hyper ate again the most oxygen. It makes more sense if I do a little series for you. So if we look at ClO, and I write cursive O's in my Cl, it's just a habit. You're going to have to live with it. The only one I bother to memorize is always the 8. So it's ClO2 minus. So if it's hypo, that's the opposite of hyper. If you think about a hypodermic needle, what do you do with that? Well, you insert it under the dermis, which is under the skin. It's where it got its name. So hypo is one less oxygen even than just ordinary chlorite. So it remains ClO. We don't put a 1 on it. But all of these are a -1 charge. That's the nice thing about them. And then chlorate ate one more oxygen than chlorite, which was ClO2 minus, and hyper ate another one still, so it becomes ClO4. All have a negative charge. So this is hypochlorite, chlorite, chlorate, and perchlorate. So that other handout I'm going to go over in grand detail hinges on this idea. So instead of knowing just that I had to give up and memorize 1, 2, 3, 4 things, I memorize 1, which is chlorite, and 3 patterns. And then, you know what else? We call these families on the periodic table. This is the halogen family. So I can substitute F, Br, or I. Maybe not F all the time because it's so small, but definitely Br and I. And I can have hypobromite, bromite, bromate, perbromate. I can make what this one little bit of memory work I've done just multiply like crazy by applying the patterns. All right, enough of that. Let's move on with what we really want to do, which is name some of these things. So first thing you have to do, and again, I'm assuming that I'm insulting your intelligence, so feel free to fast forward, is name each of these binary compounds. Well, you need a periodic table handy, so it's good for you to stop me now and go get one. And have one handy, whether you have it on a screen next to me or whether you have one on a piece of paper. But I need to understand that cesium is a metal and fluorine is a nonmetal. I look at the periodic table, opposite sides of the periodic table. It's a good hint that you have ionic substances. So this is simply named cesium fluoride. The next one is aluminum. I pause. I ask myself a question. Do I need a Roman numeral for that? The answer is no. Why not? Because it's not in the transition metals. It's over there on that clump beyond the transition metals. So aluminum chloride. And finally, lithium hydride. Don't focus on whether I capitalized something or didn't capitalize something. It's just some handwriting habits that I have. Okay, then it gets more interesting. Now I recognize transition metal, transition metal, transition metal, transition metal, transition metal. Are they trying to trick me on any of them? Silver, mercury, silver, cadmium, zinc, mercury. Mercury's here, so that one's tricky. And then no cadmium or zinc to mess me up. So everything needs a Roman numeral. So it's copper chloride. Well, I ask myself the question. Copper 1 or copper 2? Now, you do kind of need to know a little bit about what flavors they come in. Copper only comes in 1 and 2. Iron comes in 2 and 3. You do know a little bit of that. But I look at the chloride, and the chloride I know for a fact is the -1 column of the periodic table. Let's go back if you didn't know that. These are the -1s. Let me get rid of that. And these are -2, and these are -3. The 4As don't usually, they can do all sorts of stuff. They've got like split personalities. But these are primarily +1, +2, and +3 in their oxidation states. Exceptions occur. And down in here, you need the Roman numerals as your friend. Except the ones we talked about a moment ago. Silver, cadmium, and zinc. +2, +1, plus 2 plus 2 plus 1. Alright, so by reasoning backwards, the chloride is always a -1, so that's got to be a +1 copper, or this can't be a neutral molecule. So this is copper, Roman numeral 1, chloride. I put the "ide" ending on it. And then what is that? That is mercury 2 oxide. How do I know? Because I, again, work from the back. I know oxygen is always a -2. Looking at the periodic table, it's in the -2 column. So that Hg has to be the +2 variety. So that one Hg atom is +2. So that is mercury 2. Pretend that snuggles up a little better. Oxide. Okay, this one I call a 2-3 trick. That means I needed 3 of the 2s and 2 of the 3s. So I've got 3 oxygens, and they're -2 each. I've got 2 fluorines, so 3 -2s is -6. Split into 2 pieces over each of those irons means they're a +3. Or you can simply kind of do this action and go backwards. The oxygen is a -2. I know that to start with, so this has got to be the +3 variety. So I call it the 2-3 trick. I had to go to 6 to get the pluses and the minuses to cancel out. 2 of the +3s make 6, 3 of the -2s makes -6. Life is good. So this is iron, Roman numeral 3, because it's +3 iron oxide. Your good buddy rust. Then manganese, I have 2 oxygens, and oxygens are -2 each, so that one manganese is a +4. Manganese 4 oxide. And then lead comes in 2 and 4, but I know chloride is a -1, so that's got to be a +2. So my final one I'm going to write up here, lead, Roman numeral 2, chloride. Alright, if you like little charts and they help you, then I've included one here, and it's kind of a flow chart. You probably had something like this in your first year course, if you had a first year course, so I included it for folks who might be taking AP Chem as a first year course without the benefit of a previous year of chemistry. And then, let's name some more. Naming binary compounds, again, but this time give the systematic name of each of the following compounds. Okay, so now this is a mix of what all is there. So I've got cobalt, and cobalt needs a Roman numeral. I'm looking at a periodic table. I see that's in the transition metals. I know that that's a halogen, and they're always -1, so this has a +2 charge. I'm going to do this first this time. I know that chlorine is -1 as well. It's just another halogen, so that calcium has a +2 charge. But I also know that calcium's on the left-hand side of the periodic table, so it doesn't need a Roman numeral. Put RN against that one. Aluminum never needs a Roman numeral. I know aluminum is +3. I know oxygen is -2. That's my 2-3 trick. I had to get to 6. So it doesn't have any prefixes, nor does it have any Roman numerals. And then chloride, that 3 with that halogen means this is the +3 variety. It's in the transition metals. It needs a Roman numeral. So we have cobalt. I'm just going to look at them down here. We have cobalt 2 bromide. Why the 2? Because the cobalt is a +2. So that Roman numeral is telling me that cobalt is a +2. And it's bromide. Calcium chloride, no Roman numeral. Why not? It only makes a +2. It's in the 2A metals. It's all they ever make. Aluminum oxide only makes a +3. So this is all you can ever have. You can't have any other aluminum oxide. It's always going to be Al2O3. And then chromium 3 chloride got bumped to another line. So chromium 3 chloride. Well, why are they telling me that 3? That means this is a +3. That Cl is a -1, so it should be CrCl3. You should be able to translate back and forth between the name and the formula. Alright. Now, these have polyatomic ions. You need to know your polyatomic ions. Again, I send you to the separate recording about the 9 to memorize and the 3 patterns. I have mine memorized, so this is going to go pretty fast. So, this first one, I see sodium. I know it has 2 written there. I recognize SO4 as sulfate, so it's sodium sulfate. Next, I have potassium. dihydrogen phosphate, because I know phosphate is PO4 3-, and if I put one hydrogen, then it's going to go down to HPO4 2-. I put another hydrogen, it's H2PO4, and that's dihydrogen phosphate. Then I have iron 3 nitrate. Why is it 3? Because I needed 3 nitrates. I know nitrate's a -1. I know for the next one, hydroxide's a -1. I had 2 of them. It's manganese 2 hydroxide. I know that sulfite with SO3, because that's the one I've memorized, and it's a -2 charge as well. So I need 2 sodiums, and we call it sodium sulfite. Then I see carbonate, because that's one of the ones I've memorized, and I know that it's a -2, and so that's sodium carbonate. Sodium does not need any Roman numerals. Look, an H has snuck its way into a carbonate over here in G. So that is hydrogen carbonate as an ion. The H made it lose from a -2 down to a -1, which is why there's only 1 + 1 sodium with it. So that's sodium hydrogen carbonate. Lovingly also known as baking soda, and so a common name for it is sodium bicarbonate. Then this is cesium, and that's my good buddy chlorate, ClO4. Making sure that one's right. Yeah, cesium is a 1A metal. All right, then this thing, OCl, can also be written as ClO. Don't let that trip you up. Because if you write ClO3 and ClO2 and ClO4, you can just move the O. And a lot of books are going to this because the bonding really occurs through the oxygen, not through the chlorine. And so don't be alarmed if you see it written that way. So just count them up. It's ClO. So in other words, it can look just like this. It's the same critter. They're just trying to show you where the bonding is occurring. So that is going to be sodium hypochlorite. It ate the least amount of oxygens. And then I have sodium, and you just would have to know that one. That is selenite. And then I recognize this is a cousin to my chlorate, but it's Br instead of Cl, so it's bromate. So that's potassium bromate. Now, what if they're covalently bonded? Then you use prefixes, and you still use the "ide" ending as well. These are the easiest. Saved them for last. So this is phosphorus, pentachloride. Pentachloride. That's phosphorus trichloride. All right, I'm not going to write the rest. They're written down here at the bottom. So this is sulfur hexafluoride because there's 6 Fs. This, if it had a charge on it, would be sulfite, but it has no charge. It's a neutral molecule. So it is SO3 sulfur trioxide. Its neighbor over here on part E is sulfur dioxide, and then your good buddy carbon dioxide. So let's talk for just a moment about some chemistry that applies to these in particular, and any of these type as well. We call these SOx and NOx, as in socks like you wear on your feet, and NOx as in you knock somebody around. So SOx and NOx are responsible for acid rain. All of the oxides of nonmetals, when they react with water, make acids. So the sooner you embrace SOx and NOx, and you can even put in carbon compounds as well, because you know about carbonic acid. When you react those with water, you're going to make a variety of a sulfuric acid and a variety of a nitric acid, whether it's sulfurous acid or sulfuric acid, nitrous acid or nitric acid, which is a nice transition into naming acids. So naming acids is actually very easy, and the nomenclature is follows a quite elegant pattern. Hydrogen, if present, is listed first, followed by a suffix, and finally the word acid. So if the negative ion's name ends in hydro, there's supposed to be a little dash there. I don't know why it didn't print. But if it's hydro with a negative, no, there's not supposed to, yeah, there's supposed to be a dash there, sorry. Hydro with the negative root ic acid, like hydrosulfuric acid is H2S. So if it ends in ide, then going backwards, if I see hydro as the beginning of one of these acid names, I always told my students, if it's hydrosulfuric acid, that hydro prefix means caution, element approaching. You don't have to fret about polyatomic ions. So if you think about hydrochloric acid, hydrobromic acid, hydrosulfuric acid, would be realizing that's in the -2 column and you need H2. You need 2 H's. All right, if it ends in 8, then it goes to ick. If it ends in ite, it goes to us. Sulfate goes to sulfuric acids. Chlorite goes to chlorus acid. 8 ick, ite, us. It makes a goofy little sounding mnemonic device. Just recite it over and over again. 8 ick, ite, us. 8 ick, ite, us. 8 ick, ite, us. Give it a rhythm. And once again, if you like the charts, if they make sense to you and they help you as a visual learner, they're in color even to help you if you're an uber visual learner, then this just summarizes what I just took you to. Now there are some pains in the gluteus maximus. That's the backside, if you don't know your biology. These lovely little critters have been around longer than any naming system, and no one wanted to adapt and call them something else. Water falls into this category, obviously. So with the exception of the first two on the list, the AP exam either avoids them altogether or gives you the formula. But they'll tell you, like I say, they'll say phosphine, but then comma, pH 3, and carry on with the question stem. But you need to know, water, and you also need to know NH3. All right, the rest of these, they're going to give you. But hydrazine and phosphine have actual formulas. So you're not supposed to memorize those. They're going to give them to you. But I didn't want it to throw you off, because you may look at the formula first and go, that's not the translation of that chemical formula. So if I gave you phosphine and you see pH 3, you would call that phosphorus trihydride, right? When in reality, we don't even write ammonia properly. We at least write the water properly. That's the positive and that's the negative. But here, we should be writing the positive, 3 of them, for the negative, which has a -3 oxidation state. And it should be written H3N. So it's like a double whammy pain in the gluteus maximus. But that's why you have to just give up and memorize those two. All right, so let's name some acids. So now we're going to come and actually name some acids. And I'm scanning across them and I see a pattern. HBr, HBrO, HBrO2, HBrO3, HBrO4. That's a lot like HCl, HClO, HClO2 that we used as an example earlier. So instead of perchloric and chlorite and chlorite and yada yada yada, I've just got bromo in there. So this one I'm going to start with because I'm looking at the pattern of the O's here. None, 1, 2, 3, and 4. So this one was the most hyper. So that's going to be per, and it's not wrong to call it hyper, but most books are going to call it per bromic acid. So lose that prefix, and this is just bromic acid. Now, I've dropped down one more, so this is bromus. And this is below even that, so it's hypo, like hypodermic needle below the skin, below on the oxygen count here. Hypobromous acid. So what's that sucker? Well, that's just an element. So it starts with hydro. And it is hydrochloric acid's cousin. That's hard to say. So it's hydrobromic acid. So there's hydrofluoric, hydrochloric, hydrobromic, hydroiodic. It's the iodine. We usually don't talk about astatine much. It's radioactive. So we don't mess with it in lab too much, so we don't talk about it too much. But an elegant little pattern and a nice illustration of it. All right, I see HNO2 and HNO3. I recognize nitrite and nitrate. So 8 ick, ite, us. 8 goes to ick, acid, and ite goes to us, acid. So the 8 more oxygen. So this is nitric. There's nitrate ion, nitric acid. And this is nitrite, so this is nitrous acid. And there you have it. How'd I do? Love it when I get the right answers. All right, and now this is just, can you, again I'm going to hide them, can you come up with the names for each of the following compounds? Pause me. You try this one. Try it by yourself. I'll wait. No cheating. Pause me. Welcome back. All right, let's see how you did. Tetraphosphorus decoxide. Why so many prefixes? Because this is a combination of two nonmetals. That's the first question you ask yourself. Metal nonmetal or two nonmetals? Because you're never going to have metal-metal. All right, so then if it's nonmetal, happy dance, prefixes are my friend. Tetra for 4, deca for 10. A lot like geometry, don't you think? So tetrahedron, tetraphosphorus, decahedron, decaoxide. And then niobium. Where is that? That's not an element I'm very familiar with. Let's go searching. Search the periodic table. There it sits in the middle of the transition metals. So it's going to need a Roman numeral. I got to figure out the Roman numeral. So I have to go to oxygen because I know oxygen's -2. So if I had 5 of them, that means the total over here has got to be +10. And if it took 2 atoms of niobium to do that, they must be +5 each. So that's why we have a Roman numeral 5 with the niobium. Lithium, not a transition metal. It's a +1 metal. So that is just lithium. It would be oxide if that were a single O, but that's O2, so something is wrong. That's another one of those polyatomic ions that I have memorized. The O2 -2 ion is called the peroxide ion. You know, like your good buddy hydrogen peroxide. So if I'm going to use this O2 with a -2 charge with hydrogen, which has a +1 charge, I would need 2 of them. So that's hydrogen peroxide. So this is its cousin, lithium peroxide. Embrace chemical families and the fact that they have cousins. Because if you can embrace this pattern, then you get that pattern with any other 1A metal for free. All right, and then I have a metal. It's titanium. Where is that on the periodic table? It has a Roman numeral. So I have to know nitrate is -1. I memorized that one. And there are 4 of them, so there's a total of -4 on this side. So only one of these means it's got to be +4. So it's titanium, Roman numeral 4 telling me the charge, nitrate. And now we want to write formulas from names. So vanadium 5 fluoride. V with a +5 charge. Fluoride is a halogen. I know it's -1. So VF5 should be our finished product. How about B? You make it easy on me. Dioxygen difluoride. Dioxygen difluoride. Looks goofy. All right, and then what about C? Rubidium peroxide. What is rubidium? It's Rb. Peroxide. Okay, rubidium is a 1A metal, so it's a +1. Peroxide is O2 -2. So O2, but a -2 charge, so I need 2 of those. So again, it's one of hydrogen peroxide's cousins. And I didn't write it very nicely, so let me try again. That's better. And then gallium oxide. Gallium is on the periodic table right around aluminum. It is a +3 charge, whereas oxygen is a -2, so this is a 2-3 trick. So two of the galliums and 3 of the oxygens gets me to + and -6 respectively. So Ga2O3. How'd I do? VF5, O2F2, Rb2O2, Ga2O3. Nicely done. All right, so we will summarize with putting all of that flowchart together. Use this. Use this until you give up and memorize out of self-defense because you're sick of using it. But either way you look at it, most of the time on the AP exam, they're going to give you the name of the chemical and its formula. But you do, just for general purposes as an educated science student, need to be able to understand chemical nomenclature. And again, I remind you there's going to be a separate recording about the polyatomic ion business and the easy way to memorize only 9 polyatomic ions and then multiply that into a wealth of knowledge applying 3 patterns. It's also going to be good for your thinking for the AP exam. Until next time, I hope you have a great rest of your day.